Control valve sizing, core design module. The heart of control valve engineering. Control valve sizing is where process engineering, fluid mechanics, and control theory collide. More control loops fail at the sizing stage than at tuning or commissioning. Not because the math is wrong, but because the philosophy behind sizing is misunderstood. Sizing is not about making the numbers work. It is about ensuring the valve operates in a region where it can control, not merely pass flow. Sizing philosophy. Why oversizing kills control. Oversizing is the most common and most damaging valve selection error. When a valve is oversized, normal operation occurs at very low travel, small position changes cause large flow changes, effective valve gain becomes excessive, resolution and repeatability collapse, stiction and hysteresis dominate behavior. From a control standpoint, an oversized valve behaves like an on-off device disguised as a modulating valve. The controller is forced to hunt because the valve is too powerful relative to the process. A valve that can pass maximum flow is not necessarily a valve that can control maximum flow. Why undersizing kills capacity. Undersizing is less common but equally dangerous. When a valve is undersized, it operates near full open at normal loads. Control authority disappears during disturbances. Maximum production rate is capped. Pressure recovery and velocity increase erosion risk. An undersized valve limits plant throughput and removes the controller's ability to correct deviations during upsets. Design versus normal versus minimum flow points. Proper sizing is never done at a single operating condition. Design flow. Maximum expected flow ensures capacity and availability, usually 10 to 20% above normal. Normal flow, most frequent operating point, should lie between 40 to 70% valve travel, primary determinant of controllability. Minimum flow, startup, turndown, or idle conditions, determines low-end resolution and stability, often ignored and later regretted. Good sizing ensures control at normal flow, authority at minimum flow, and capacity at design flow simultaneously. Liquid sizing, IEC method. Image, CV definition, and physical meaning. CV is not a valve size, it is a hydraulic capacity parameter. By definition, CV equals flow rate of water, US GPM, producing a 1 psi pressure drop at 60 degrees Feflers. Physically, CV represents effective flow area, internal geometry efficiency, energy dissipation capability. Two valves with the same line size can have vastly different CV values. Required process inputs. Accurate liquid sizing requires realistic process data. P1, inlet pressure, P2, outlet pressure, delta P, pressure drop across the valve, GF, liquid-specific gravity, vapor pressure, determines cavitation risk. Errors here propagate directly into poor controllability or mechanical damage. Choked flow and cavitation limits. Liquids can choke, not by sonic velocity, but by vapor formation. Key phenomena. Cavitation. Vapor bubbles form and collapse downstream. Flashing. Liquid permanently vaporizes downstream of the valve. Design implications. CV equations must be corrected for pressure recovery. Valve selection must limit internal pressure drops. Severe service trims may be required. Ignoring cavitation limits leads to noise, vibration, trim destruction, and unstable control. Gas and steam sizing image. Compressible flow fundamentals. Gases behave fundamentally differently from liquids. Density changes with pressure and temperature. Flow accelerates as pressure drops. Energy conversion dominates flow behavior. Sizing must account for these compressibility effects. Sonic velocity and choking. Gas flow becomes choked when velocity reaches the speed of sound at the vena contracta. Once choked, flow rate becomes independent of downstream pressure. Increasing delta P does not increase flow. Control authority diminishes rapidly. Choked flow is a physical ceiling, not a control limitation. Expansion factor Y and pressure recovery. The expansion factor corrects for gas density changes through the valve. Design considerations. High pressure drops reduce Y. Low Y reduces effective CV. Valve geometry strongly affects recovery. Incorrect Y estimation leads to valves that look fine on paper, but starve the process in reality. Image. Flashing versus cavitation. Although related, these are fundamentally different regimes. Cavitation, reversible vapor formation, damaging. Flashing, irreversible phase change, erosive. Valve sizing must avoid cavitation when possible, manage flashing with appropriate trim and materials. except that flashing cannot be eliminated, only controlled. High-pressure drop services. High delta-P services concentrate enormous energy inside the valve. Design implications: multi-stage trims may be required. Velocity must be limited. Valve body and trim materials become critical. Actuator thrust requirements increase significantly. Control valves often act as energy dissipators, not just flow regulators. Noise-driven sizing constraints. Aerodynamic and hydrodynamic noise is not a comfort issue, it is a mechanical integrity issue. Excessive noise indicates extreme turbulence, shock wave formation, accelerated fatigue. Noise constraints often force larger valve sizes, reduced allowable pressure drops, specialized low-noise trims. Ignoring noise rising leads to piping failures, instrument damage, and chronic maintenance issues. Control valve sizing is not a spreadsheet exercise, it is systems engineering. When sizing is done correctly, the valve becomes invisible and the loop feels effortless. When it is done poorly, every downstream problem, oscillation, wear, noise, instability, can be traced back to this single design decision. Actuators and force-torque engineering, making the valve move correctly. If valve sizing defines what the valve must handle, actuator engineering defines whether the valve can actually do it. Many valves are mechanically perfect, yet fail in service because the actuator was treated as an accessory rather than a load-bearing control machine. Actuators do not merely move valves, they determine speed, stability, fail behavior, and long-term reliability of the entire control loop. Actuator types. Image. Spring-diaphragm actuators. Spring-diaphragm actuators are the most widely used actuators in process control due to their simplicity and inherent safety behavior. Key characteristics: pneumatic signal opposed by a mechanical spring, linear force output proportional to diaphragm area and air pressure, natural fail-safe action via spring return, smooth, stable response for modulating control. Design strengths: excellent for globe valves and small to medium rotary valves, predictable behavior and low maintenance, simple force calculations. Limitations: limited thrust capability, large physical size for high force applications. Spring force varies with travel, affecting available thrust margin. These actuators are preferred where control quality and fail safety are more important than compactness. Piston actuators. Piston actuators use air pressure acting on a piston to generate high thrust or torque. Key characteristics: much higher force density than diaphragm designs, double acting or spring return configurations, suitable for high pressure drop and large valve sizes. Design strengths: compact for high force requirements, consistent force across stroke, ideal for severe service and rotary valves. Limitations: more complex sealing, higher air consumption, fail-safe action requires large springs or accumulators. Piston actuators dominate where force requirements exceed diaphragm capability. Electric and electro-hydraulic actuators. These actuators replace compressed air with electric power, sometimes coupled with hydraulic amplification. Key characteristics: precise positioning capability, independent of plant air systems, suitable for remote or hazardous locations. Design strengths: high torque availability, good for slow-moving or infrequently adjusted valves, useful where pneumatic infrastructure is absent. Limitations: slower response for modulating service, fail-safe action is complex and costly, sensitive to power reliability and environmental conditions. Electric actuation is typically selected for positioning and isolation, not fast regulatory control. Actuator sizing principles. Image actuator sizing is fundamentally a force or torque balance problem. The actuator must overcome all resisting forces throughout the valve stroke under worst-case conditions. Force balance in globe valves. For linear valves, actuator force must exceed differential pressure force on the plug, seat load required for tight shutoff, packing friction, stem and trim friction, dynamic flow forces. Critical insight: maximum force requirement often occurs at shutoff, not during throttling. Packing friction increases significantly with temperature and aging. Unbalanced trim dramatically increases required thrust. Design rule: the actuator must deliver sufficient force at minimum supply pressure, not nominal pressure. Torque balance in rotary valves. For rotary valves, the actuator must supply torque greater than dynamic flow torque, seating and unseating torque, bearing and seal friction, breakaway torque after idle periods. Torque characteristics are highly nonlinear. Peak torque often occurs near closed position. Flow-induced torque varies with valve angle. Seat wear changes torque requirements over time. Rotary actuator sizing failures almost always trace back to underestimating breakaway or seating torque. Seat load, packing friction and unbalanced forces. Seat load ensures tight shutoff but directly increases actuator demand. Design trade-offs: higher seat load, better shutoff, higher actuator force, tighter packing, lower leakage, higher friction, balanced trim, reduced force, reduced shutoff margin. Ignoring these interactions leads to valves that throttle well but cannot shut off reliably, or valves that shut off tightly but cannot modulate smoothly. Fail action and safety design image. Fail action defines how the valve behaves during loss of motive power. This is not a control decision. It is a process safety decision. Fail open versus fail closed logic. Fail action selection depends entirely on process risk. Typical logic: fail closed, protect downstream equipment or prevent release. Fail open, prevent overpressure or overheating. Fail in place, used where sudden movement is more dangerous than loss of control. The correct fail position is the one that leaves the process in its lowest energy, safest state. Air failure scenarios. Loss of air is the most common actuator failure mode. Design considerations. Spring return actuators move to fail position automatically. Double-acting actuators require air reservoirs or accumulators. Positioners must vent correctly to avoid delayed response. Fail behavior must be validated under gradual air loss, sudden air loss, partial pressure conditions. Assuming ideal failure conditions is a frequent design mistake. Spring selection and safety margins. Spring selection is critical to reliable fail action. Key principles: spring must overcome maximum process force plus friction. Safety margin must account for aging and corrosion. Spring force must be sufficient at end of stroke, not mid-stroke. Undersized springs cause incomplete fail movement, delayed shutdown, dangerous intermediate valve positions. Actuator safety margins are not optional. They are the last line of defense between process control and process hazard. Actuators are not passive accessories. They are force machines operating against live process energy. When actuator engineering is done correctly, valves respond decisively, fail safely, and disappear into the background of plant operation. When it is done poorly, even the best valve design becomes unreliable, unsafe, and uncontrollable.